next speaker, Monika Aidelsburger, also from Munich, actually just next door to me, who will talk on Floquet physics. Monika.
Yeah, thank you very much. I'd also like to thank the organizers for having me here and giving me the opportunity to present our work. This is very much in the spirit of the previous talk from Antoine, now here with cold atoms in lattices, where we are aiming at engineering topological physics in our lattice models. And just as a very brief motivation, we have all these beautiful results from condensed matter systems where different types of topological systems have been studied in 2D, but also in 3D. And this is really inspiring for doing quantum simulations in our platforms. But what I'm going to talk about today is work that we have done during the last year and also this year, where we were asking the question if we can use the techniques that have been developed to engineer topological physics and band structures and go beyond, in a sense, that what we can engineer is not easily found in static condensed matter realizations. And just very brief introduction and how our system looks like. I already mentioned we work with ultra-cold atoms and optical lattices. So in a very abstract sense, we can think about these systems as being nicely isolated from the environment and the dynamics being described by Hilbert models. In our case, we work with bosons. So we work with the Bose-Hilbert model. And so we have the kinetic energy term with hopping matrix element J and an interaction term with Hilbert interaction energy U. Now, for all the experiments I'm presenting today, we are in the very weakly interacting regime and we work with Bose-Einstein condensates. So this allows us actually to prepare wave packets that we can then describe in semi-classical dynamics. So we associate a mean position and mean quasi-momentum to our wave packet, and then we can manipulate the dynamics of the system by applying external forces, for instance, to our cloud, and then measure the dynamics in situ by tracking, for example, the center of mass motion. And this will allow us to characterize and study the band structure and the geometric properties of the lattices that we engineer in the lab. Now, starting from this type of lattice systems, typically these band structures that we get, the Bloch bands, are topologically trivial. So very much in the light of the previous talk, we have to figure out ways in order to make them non-trivial. And the way we are doing this is via periodic driving or Floquet engineering. So the essential idea is that we take our Hamiltonian and we vary it periodically in time, for instance, by varying the tunneling matrix element periodically in time. That is, we generate a Hamiltonian that is explicitly time dependent, as shown here, where the driving period is denoted as capital T and is 2 pi over the driving frequency. Now, if we have such a Hamiltonian, we can look at the stroboscopic time evolution of the system. This means we probe the dynamics of the system at integer multiples of this driving period. And if we write down the time evolution operator for the stroboscopic dynamics, we can express it in this form, where the time evolution operator, he describes the evolution after one driving period. And I can always find time-independent Hamiltonian HF, our Floquet Hamiltonian, that governs the stroboscopic dynamics. Now, generally, it's not so easy to write down analytic form of this Hamiltonian, but in particular in the high driving frequency limit, so where omega is the largest energy scale in the system, we can find a series expansion in powers of 1 over omega, where then to lowest order the Hamiltonian will be nicely approximated by the lowest order in this 1 over omega power series expansion. So then we can implement or write down different modulation protocols and compute this effective Floquet Hamiltonian in order to find a technique that allows us to engineer bands with non-trivial topological properties. Now, this time periodicity comes with a quasi-energy spectrum. So it means that the quasi-energy in our system is actually only defined up to integer multiples of the driving energy quantum h bar omega. So if I use this technique in order to engineer a certain band structure, as for instance shown here as this cosine dispersion, I essentially have infinite copies of these dispersion relations that are spaced by h bar omega. Okay, so we should keep that in mind. It will be important for how we engineer the non-trivial topological properties in driven systems that have this modified bulk edge correspondence we are interested in. And for most of the time, I will actually show the reduced Floquet Brillouin zone, meaning that I define the quasi-energy within minus h bar omega half and plus h bar omega half. Okay, so these Floquet engineering techniques have been actually successfully implemented in order to engineer a variety of topological lattice models, also to measure chiral currents in ladders, for instance, as has been introduced by Antoine on this three-side system. And the idea was really to use this periodic driving technique in order to emulate the topological physics that have been found in condensed matter systems, for instance, in quantum Hall type systems. So in a high frequency limit, we can actually take the rotating wave approximation and then map it onto a static Hamiltonian. And in the static realizations, we know how to characterize the topological properties of the energy bands in 2D systems in particular. And here's a reminder of the quantum Hall, the quantized Hall conductance measurement, which is one of the works that really has inspired all of the subsequent works we have done in the lab. There we can characterize the topology of the bands by computing these Chern numbers, as has been introduced before, integer numbers that characterize the topology of the band. And now it turns out that if we know all the Chern numbers that characterize the bands, we also know how many edge modes are at an interface between two distinct topological phases, for instance, between a topological insulator and the interface to vacuum. So that sum of the Chern numbers of the occupied electron bands also determines the number of edge modes that we can have in the system. But now this can be modified and leads to a generalized bulk edge correspondence in periodically driven systems. And here this goes back to the quasi-energy spectrum that I've mentioned before, which tells you that the energy at h bar omega half is actually equivalent to the one at minus h bar omega half, as we also know from quasi-momentum spectrum in spatially periodic systems. Okay, so this means now that I can have an edge mode that enters from below and leaves from the top. And this is really only possible because we have no true notion of a lowest energy band. In a static system, I cannot have an edge mode that is winding around the energy spectrum. And this leads to interesting new topological regimes that are called Anomalous Floquet regimes. In particular, I can have a system where the Chern number of the band is equal to 0, but nonetheless I have this non-trivial edge modes due to this non-trivial winding of the energy spectrum. And this also means that I can have new interesting properties in the presence of disorder, for example, where the bulk energy bands are completely localized, but nonetheless I can have robust edge transport in these anomalous systems. So in our lab, we realize them in periodically driven honeycomb lattices. But before I introduce the system, let me first tell you what the new topological invariants are that characterize the properties of these periodically driven systems. We know from static systems we can compute these Chern numbers, and they are actually related to the number of edge modes above and below the band. They are given by the difference between the two. But now, since we have seen that the Chern numbers are not enough in order to compute the topological properties, we have to add new ingredients. And the way we do that is by defining winding numbers that characterize the topology of the energy gaps. So now we have introduced these winding numbers W0 and W pi that determine the net number of edge modes in the gap. And again, the Chern number is given by the difference between the winding number above and below the band. But in contrast to Chern numbers, here for this two-band model, we have two independent quantities characterizing the properties, while the Chern number would be actually only one independent quantity because the sum of the Chern numbers has to be equal to 0. Okay, the goal of our experiment is actually to realize this anomalous regime and to measure the winding numbers in the experiment. We work with bosonic potassium atoms, so we prepare Bose-Einstein condensates in our lattices, and in particular we work with honeycomb lattices as sketched in these three potentials that display 3 different instances in time during our modulation protocol. And what we do is we increase the hopping matrix elements periodically in time along these red bonds. And we can implement that in our experiment by modulating the intensities of the laser beams. So the hexagonal lattice or honeycomb lattice is generated by interfering 3 laser beams. And if we vary the intensity of these laser beams periodically in time, we exactly realize these potentials that are shown up here, where the tunneling amplitude is then modulated in this chiral manner. And there are a variety of different topological regimes that we get in the phase diagram if we plot it as a function of the modulation frequency and the modulation amplitude. And I will briefly go through 3 of them, which we have characterized in more detail in the experiment. In the high frequency limit over here, so when the driving frequency is very large, we realize the well-known Haldane phase or Haldane regime, where we can generate topological bands with Chern number plus and minus 1 when edge mode lives around 0 energy in this quasi-energy spectrum. Now, if we reduce the modulation frequency further and further, what happens is actually that there's a gap closing point between Floquet zones. And the gap closing marks the topological transition, the topological phase transition, which changes the Chern number of the system. And because it happens between Floquet zones, it generates an edge mode in between 2 Floquet zones. So now we have 2 edge modes, one at pi and one at 0 energy, and the Chern number of the 2 bands is equal to 0. So this is what we call the anomalous regime. And then if we decrease the modulation frequency even further, we enter another Haldane type regime where again the Chern number of the band is plus and minus 1, but now we have had a gap closing point around 0 energy, which had eliminated the mode, the edge mode that we had originally at 0 energy. Now, the first thing to probe this phase diagram is to track the topological phase transition points, which we can do by measuring the energy gap between the 2 bands in our system, which we do along this white line. And the way we do it is by interferometric measurements. So we prepare a wave packet at a certain position in quasi-momentum space. And then we apply a force to our cloud, which if it's large enough and we can move it across this avoided crossing in the band structure, we can create a coherent superposition between a fraction of the band in the excited state and a fraction in the lowest band. And then we move it up to a certain point, capital Q, where we introduce a certain hold time that is variable. Then we hold there for a certain amount of time and close the interferometer again by moving back. So we reverse the direction of the force, we mix the levels again, and then we measure as a function of time the fraction of atoms that ends up in the lowest band. And if we do that, we find this oscillation, and the frequency of this oscillation then directly determines the energy gap difference between the 2 bands. Okay, so we do that across this white line that is shown in the phase diagram. And this is one of the examples of measurements that we get. Here you see the measured energy gap, and the solid line is a band structure calculation without any free parameter. And you see that we have a finite energy gap up to a certain point where we see that it vanishes, and then it increases again, and we find a second gap closing point. And these 2 mark the topological phase transitions between the different regimes that I've introduced before. So this gives us a first hint about where the Haldane regime and where the anomalous regime is in our model. Now, this interferometric technique in principle would allow you to measure any of the energy gaps between the different Floquet bands. I've told you that we have this infinite series of bands, but due to the stroboscopic nature of our measurement, remember that the Floquet Hamiltonian only describes the stroboscopic evolution of our system. It turns out that we actually always measure the smaller one. And now if we start in a high frequency limit where h bar omega is very large, it means that the energy difference around the pi gap is much larger as compared to the energy difference around 0 energy. So if we start in the high frequency limit, we actually know that we measure the energy gap around 0 energy. And then if we decrease the modulation frequency in order to enter the different topological regimes, we will find that there's a transition, or there's a point where these 2 become exactly equal. And at this point, they have to be equal. So the sum of the 2 has to be equal to h bar omega. At this point, actually, the notion between the 2 gaps changes, and we start to measure the energy gap around pi, so between Floquet zones. And this you can see as this cusps in the measurement that I've shown you previously. This cusp actually occur exactly at h power omega half. So we can read off this diagram that on the right, we start measuring the energy gap around 0 energy. Then the notion changes, we start to measure the energy gap around pi, and then again, we start to measure the energy around 0. So this actually means that from this simple measurement, we can already deduce which one of the energy gaps is closing in the spectrum. And this will be important for determining how the winding numbers change in our system. So this is the first important point to remember, that we have a way to identify where the gap closing point occurs. Okay, and then the idea is, in order to track the topological properties of our system, to start in a well-characterized high-frequency limit, the Haldane regime, where we know what the topological properties of the phase are. That is, we know that the Chern number of the two bands is plus and minus 1. There's an edge mode at 0 energy, and there's no edge mode between Floquet zones, because we also know that we can map it to a static system via the rotating wave approximation. And then the idea is to track how the topology of the band changes across the topological phase transition points. So we characterize the geometric properties of these gap closing points. And just as a quick reminder how the biotopological properties are defined, here's the definition of the Berry curvature, which is defined as the winding of the cell periodic Bloch functions across the Brillouin zone. And the integral over the Berry curvature then defines the Chern number of a certain band. And here mu is the band index of a particular band. There's a variety of different methods that have been developed over the past years in order to extract these topological properties and geometric properties also of driven band structures, and you can find them in this review paper. Here I just want to discuss briefly the technique that we have been using. The idea is again to work in a semi-classical description, that is, we prepare a wave packet with a well-defined mean position and mean quasi-momentum. And then we applied a force to our atomic cloud again to move it in quasi-momentum space. This time, however, adiabatically, meaning we preserve the band population during this process. We don't excite a fraction of the atoms to the higher lying band. And then we characterize the anomalous transverse velocity that we obtain when moving the cloud through a region in reciprocal space that is characterized by a non-zero Berry curvature. And this allows us to then probe a region of Berry curvature that is concentrated in quasi-momentum space. So if we look at this white line across our phase diagram again, this parameterizes a family of Hamiltonians where we can characterize the topological properties just before and after the phase transition point. So what we do, and there's an example shown here. Here you see the Berry curvature of the lowest band just before and just after such a phase transition point, which occurs at this gamma point in the center of the Brillouin zone. And there we see that just before there's a pi Berry flux developing around the gap closing point, which flips sign just after the phase transition point. And this is what we characterize by looking at the anomalous transverse velocity, which occurs in our measurement as a center of mass deflection. So what we do is we prepare a quasi-momentum wave packet at this position M, for instance, in the Brillouin zone, and then we move it across the gamma point where we know that the gap closing happens. And then we measure the center of mass motion or the transverse deflection in situ after we have performed this motion in reciprocal space by applying a force. And then depending on the sign of the Berry curvature that is concentrated around the gamma point, we will either see that the cloud gets deflected to the left or to the right. And it turns out that actually the sign change of this measurement, so if the deflection flips from positive to negative or from negative to positive, defines what's the topological charge of this gap closing point. And this topological charge then is directly related to the change in the winding number in a certain gap. And for that, we need to also know which one of the two gaps is closing in order to infer which one of the two winding numbers is changing, if it's the one around 0 energy or the one around pi energy. And here you see the result of such a measurement. we start again in the high frequency limit, where we again know that the winding number around 0 energy is equal to 1, and the winding number around the pi energy gap is equal to 0. And we move our cloud through the gap closing point, which happens at gamma, so in the center of this Brillouin zone. And here you see an example for certain parameters of our model. And you see that the deflection that we measure is positive, but very small. So this you can actually not see in this Berry curvature plot, but there's a small positive Berry curvature at the gamma point. Now, if we move towards the topological phase transition, we see that there's positive Berry curvature developing around this gap closing point. So this is the associated pi Berry flux, which then changes sign just across the phase transition. And this we see as the sign flip of our deflection that we measure by tracking the center of mass motion of our cloud. And now from the previous energy gap measurement, we know that the gap closing point occurred between Floquet zones. So we know the winding number between Floquet zones is changing. And from the sign flip, we can infer that it's changing by +1. So this is indicated down here. The winding number W pi has changed from 0 to 1. And we know that for a finite system, there now would be an edge mode also in the pi gap for our driven system. Now, the second phase transition point behaves very similar. Now, in this second region, the deflection increases again, it becomes positive. And just before the phase transition point, we see positive Berry curvature developing at the gamma point, which then flips sign if we move across the topological phase transition. Now, from the previous measurement, we know the energy gap has closed around 0 energy, which means we know that the W0 has to change across this phase transition point. And from this sign flip, we can infer that it changes by -1. So it goes from 1 to 0, and we have eliminated one edge mode around 0 energy. And the reason why, despite the fact that these two flips look the same, we have different changes in the winding number, is because we have to always define it with respect to the band that lies below the gap closing point. And here in this measurement, we have chosen to measure the lowest energy band. Okay. So from these two combinations, the energy gap measurement and the deflection measurement, we are able to extract the full set of topological invariants, which are the winding numbers, which allow us to identify that in the large driving frequency limit, we are in the Haldane regime, and for lower frequencies, we enter the anomalous regime. And with this, I'm at the end of my presentation, and I'd like to thank all the people that have contributed to this work. And in particular, I want to thank Karen and Christoph, who did all the nice work in the lab. And now starting from there are a lot of interesting physics that we are interested in studying. In particular, we are trying to see the edge modes directly in a finite system in our lab. And we are very interested in studying the interplay with disorder, which is expected to be very different in conventional quantum Hall systems as compared to anomalous Floquet systems. And with this, I also would like to thank all the other people, and in particular, thank you for your attention. Thank you very much, and I'm happy to take any questions.
All right, thanks a lot, Monika, for the nice presentation. There are no questions in the chat yet, so I'll start again, like in Antoine's case. So there's these two modulation schemes, the amplitude modulation, where you modulate the tunnelings in a circular fashion, and there's the circular shaking also that people have been using. So can you say something about advantages and disadvantages of both schemes?
Yes, so actually this anomalous regime exists in both cases. In the circular modulated case, you should also introduce a sublattice energy offset between A and B sides in order to enter this phase. And from the numerical simulations that we have done, there's just experimentally or technically one maybe disadvantage of the circular modulation scheme because, well, the phase modulation scheme, because the energy gaps are a little smaller than what we have in our amplitude modulated.
Okay, here's one question actually by Maren Bukov, who we know very well. Okay, on the phase diagram, gap versus drive frequency, cusps signify the phase transitions. It seemed to me there are a few extra kinks, non-analyticities, even within the same topological phase. what is happening at these points. So I think
Okay, so let me just show the slide again. Can I do that myself actually, or does someone has to do
and we can see them again now.
that? Okay. So I think you are referring to these points here where we see this little kinks. This is actually due to, I didn't mention that, so this is actually due to coupling to even higher bands. So this calculation was done for 6 bands. And depending on the drive frequency, you can have higher photon couplings. So there are 2 h bar omega, for example, resonant with a higher band. Like this you see here, this very narrow avoided crossings.
Okay, very good. Looking if any other questions are coming in. So maybe you can say something about the prospects for doing interacting physics in these systems, or what would be the interesting phases to observe in these topological systems, or especially in the ones, the non-trivial ones where you have basically edge states but zero Chern number. What would be interesting?
Well, so what we would like to study is actually the interplay with disorder, because you can show that actually for conventional quantum Hall systems, if you introduce disorder, there is, of course, transition to a trivial regime if the disorder becomes large in order on the energy gap between the 2 bands. And then there's also no non-trivial transport around the edges anymore. But in these anomalous Floquet systems, if you introduce disorder due to the fact that the edge mode is protected by the quasi-energy winding, even if all the bulk states are completely localized, there's still robust edge mode transport. This has been predicted. And now this is interesting also from this perspective of interacting systems, because if this indeed happens, that we can have a completely localized bulk but non-trivial edge transport, it offers the possibility that there are also many-body localized phases that exist in this periodically driven system, where indeed we can have a many-body localized bulk but non-trivial edge transport in the system. So this is something that would be very nice to see, which is very characteristic of these anomalous Floquet systems, and would be one of the first systems that allows us to do many-body driven systems with non-trivial topological properties, which so far is still an open goal.
All right, very cool. I see no more questions at this point. So thanks, Monika, also for the very nice talk. And let me make some final comments. So thanks a lot, everybody, for the great talks in this mixed session on quantum communication and quantum simulations with quantum many-body systems, with a great lineup of excellent speakers. I hope all of you enjoyed the talks, found them interesting, stimulating, and of course, you can get into contact with any of the researchers also directly if you have any follow-up questions. With that, I also say thanks from my side. Goodbye, everybody, and enjoy the talks that are coming up in the other sessions. Bye-bye.